Okay, today we're going to be looking at linear approximation, or another word for it is linearization. And the idea behind linearization is just finding the equation of the tangent line. We've done this so many times already throughout this year. We're basically finding the equation of a tangent line, and we know that the equation of a tangent line both needs a point and a slope. And once you have the point and the slope, you can then write it in y minus y1 equals m times x minus x1 format. The only extra added piece to this now is once you write your equation of the tangent line, we're basically going to solve for the y value, and we're going to make y turn into an L of x. So let me show you what that looks like. If we have y minus y1 equals m times x minus x1, I'm going to add y1 onto both sides, and then that y value is just going to turn into an L of x. And let me scroll up here. So this becomes L of x equals m times x minus x1 plus y1. And the reason why we use L of x is it just kind of signifies to the reader that we are using this equation of a tangent line to then do a linear approximation of a value that is really close to the curve itself. And we're just estimating a value pretty close to the indicated number that we know. So for example, let's say we know this point A, f of A. We're just using the tangent line to say, well, I want to approximate what this value is. And so a tangent line, you'll notice, is very, very close to it, right? It's very, very close, just slightly above it. And so it's giving you a good estimate for what this value of f of x is if you don't know what that f of x value is. Okay? So as we scroll through this page here, you'll notice that the main gist here is that we write our linear approximation in the form of y minus y1 equals m times x minus x1. We just move the y1 over and turn that y into an L of x. That's basically it. Okay? Let's go ahead and take a look at a few problems on the next page. So here in example 1, we want to find the approximate value of square root 26 without using a calculator. So you'll notice that in the main gist of it is you want to say, okay, what is square root 26 really coming from? Well, that's basically a square root function. Let's call it square root of x. And you'll notice on the graph to the right, this is actually the function square root of x. And what we want is, okay, well, where is root 26? I know my roots. It's pretty close to the value of 25. And so when I'm at 25, I know that root 25 gives me the value of 5. Okay, so we're going to use that knowledge to then say, okay, if I want to find the tangent line approximation, I'm going to draw the tangent line to the curve right there. And I am drawing it slightly above the point just so that you can see what's going on here. Do know that that red line should really more rest on the graph itself, okay? But what we need here, again, is that point and the slope. We obviously see that the point is made up of f of 25, the point 25, gives us the y value of 5, or in other words, the point is 25 comma 5. However, we do need the slope, and to find the slope, what we're going to do is take the derivative of our function. Okay, so f prime of x is equal to, and then since that is x to the half power, we're going to turn that into 1/2 x to the negative half, or that's the same thing as 1 over 2 root x. Since we need to find the slope at this actual point, at 25, we're going to plug f prime of 25 in and get 1 over 2 root 25, or that's the same thing as, 5 times 2, so we get 1 over 10. So our slope is 1/10, and our point is 25/5. Let's put that into our linear approximation line, and remember, it's really just the tangent line itself. So we write y minus y1 equals m times x minus x1, and I'm just going to fill in the missing information. Our y value is 5, our slope is 1/10, and our x1 value is 25. As I move the numbers around, I'm going to get L of x is equal to 1/10 x minus 25 plus 5. This is the equation of your linear approximation line, just like that. And at this point, let's go back to the question. It says find the approximate value of root 26. So now this is where we plug in 26 into your linear approximation line. So 26 minus 25, that will just give us 1. 1 times 1/10 is 1/10, and add 5. So what we're saying here is that L of 26, which is basically what we're saying is root 26, is about equal to 5 and 1/10, or I'll just write it as 5.1. Okay, so that's our approximation right there. So what it's saying is if I were to look at 26 here, that right here, this is the value of 5.1. Now, what is the actual value? Are we pretty close to the approximate value? Let's take a look at our calculator and see what happens. If we were to actually do square root of 26, that's a value of 5.099. So the actual value of root 26 is 5.099. You'll notice that our number was really, really close to it. That's exactly what we're doing. We're getting an approximation of the true value without actually needing a calculator for this. Now what you'll notice is that number 5.1 that we found, it was a bit of an overestimate. I'm going to write down the word overestimate here. Okay, this is an overestimate to the true value, and you'll notice that the line itself, it was slightly above the actual curve of the graph of the square root function. So because the tangent line is above the actual curve, that's going to give you an over approximation. Actually, let's tie it in with what we've learned about in the past. If you recall, we can say that if we take the second derivative, the reason why we want to find the second derivative is, remember that second derivative determines concavity. And so if we take the second derivative, we're going to get negative 1/4 x to the negative 3 halves power. Now, because the x value is always positive numbers, 25, 26, 27, and so on, when you plug in those x values, you'll notice that the second derivative will always be negative. Because the second derivative is negative, that's showing you that the graph is concave down. If the graph is concave down, then the tangent line approximation will always be above that concave down graph. Therefore, it shows you that this is going to be an over approximation, an overestimate. So that's something to keep in mind as you're solving these approximation problems. You want to find out if it's an overestimate or potentially an underestimate. Let's go ahead and take a look now at example 2 and see what's different about this problem. Okay, so let's start off with the function itself. F of x is 2x cubed minus 3x. And so we need to find the actual point. Remember, what we want is a point and a slope. So the point itself is, if you plug in 1, we get 2 times 1 cubed minus 3 times 1, or that's going to give us 2 minus 3, or negative 1. So we get the point 1, negative 1. And don't forget that we also need to find the slope, and the slope is found by doing the first derivative. Our derivative is going to equal 6x squared minus 3. Since we're doing our tangent line approximation at the value of 1, let's find the slope actually at 1. So if we plug in 1, we're going to get 6 times 1 squared minus 3, or the slope at 1 is a value of 6 minus 3, that'll give us 3. Let's go ahead and write our tangent line approximation now. So y minus y1 equals m times x minus x1, and let's fill in the missing numbers. y1 is negative 1, m is 3, and x1 is 1. So moving a couple of things around, we see that this is really plus 1, but to move it over, we're going to get 3x minus 3, and then we're going to have to subtract 1 to move that 1 over to the other side. In its final form, remember that y is the same thing as L of x. Don't forget to write it as L of x is equal to 3x minus 4 That right there is our tangent line approximation. Let's use our tangent line approximation to now find the value of 1.1. So L of 1.1 is equal to 3 times 1.1 minus 4, or that's the same thing as 3.3 minus 4. And 3.3 minus 4, that's going to give us about negative 0.7. So what we're finding is that when we're at 1.1, we're roughly around negative 0.7. What do you think? Is this an over approximation or an under approximation? Well, to do that, let's go with the second derivative. If we find the second derivative, that says 6x squared, so we'll get 12x is the second derivative, and at the actual value of 1, the second derivative is going to give us a positive number. So because the second derivative is a positive number, we know that this graph is concave up. Therefore, if we draw a tangent line approximation to anything that is concave up, you can actually see, oh no, look at that. Our tangent line is below any points that are relative to the actual curve itself, to the actual graph. Therefore, because the tangent line is below the curve, this is going to be an under approximation. Okay, so there we go, an under approximation. Let's examine this graphically actually and see how this is going to be an under approximation. So our equation is 2x cubed minus 3x. Here we go, Desmos. And we're going to graph 2x cubed minus 3x. Alright, and our main focus right now, let's see here. There we go. Our main focus is at the value of 1, right? So if I were to, let's see here. Screen right. Okay, so if I were to show you right here at 1, we can see how the tangent line would look something like this, right? And so since our tangent line is below the curve itself, that the value of 1.1 is giving you that under approximation. So we did get a value, but it wasn't the exact value, it's just an under approximation to the true value that actually exists. Okay? Alright, so I hope that graph helped clarify some things. Hopefully it makes sense to you. Alright, let's go on to our last problem. By approximately, how much does the area of a circle change when the radius increases from 4 inches to 4.01 inches? Well, we know that the area of a circle is given by the formula A equals pi r squared. So let's figure out a couple things. First of all, let's find the derivative of A. The derivative of A tells us the area changing, right? It's the rate of change of area. And so we'll get 2 pi r. What we're doing is we're thinking about how as the radius changes, we want to determine the area. And since our equation is pi r squared, we've got this value at 4, and it's giving us a particular area of, well, let's plug in 4, right? So if you plug in 4, the slope itself, a prime of 4, is equal to 2 times pi times 4, or that gives us 8 pi. That's basically our slope. Let's also find the actual point. So if we were to plug in a of 4, then we get pi times 4 squared, or that gives us 16 pi. Again, let's write this in its tangent line approximation form, which is going to be y minus y1 equals m times x minus x1. And our values are, the y value itself is the a, which is 16 pi. The m, the slope, is 8 pi. X minus, and this is when the x value is 4, just like that. Moving a couple things around, we see that the L of x is equal to 8 pi times x minus 4 plus 16 pi. I'll actually leave it in that form right there. Okay, that way it'll be a lot easier, because what we need to do is actually figure out what is that area when it's actually 4.01 inches, right? So let's go ahead and plug in 4.01. 4.01 will give us 8 pi times 4.01 minus 4 plus 16 pi. 4.01 minus 4, that'll give us 0.01. So you're talking 0.08 pi plus 16 pi. Okay? And that's the value of 4.01. Now, let's read the directions again. It says, by approximately how much does the area change as you increase from 4 to 4.01 inches? This is 4.01 inches. And what we want to do is take away, we're going to, basically, I'll do this in a different color. We want to take away the actual area at the value of 4, because we want to find the change, right? It's saying, how does the area change? So we want to do basically the idea of A of 4.01 minus A of 4. Well, we already have A of 4.01, that's this. Subtract A of 4. What is A of 4? That's the true value we found already, right? That's the 16 pi. So if you subtract 16 pi, then these really just go away. And so the change in area that we're looking for is basically 0.08 pi, like that. Let's see what that value actually is. Okay, so 0.08 pi is a value of 0.2513. I'm just going to go ahead and write that down. We're getting about 0.2513. Again, I just want to make a comparison. How does our approximation of the change in area relate to the actual change in area? So to do the actual change in area, remember what we can do is the area of 4.01 minus the area of 4. And so if I actually plug in 4.01 into our pi r squared formula, and then plug in 4, right, which is 16 pi, just like that. Let's see what we end up getting. So we do 4.01 squared minus 16. Let's do that. Let's see here, enter. So 4.01 squared minus 16, that gives us 0.0801. So this is actually 0.0801 pi. This is the actual number, and remember that what we found here was an approximate answer of 0.08 pi. So you'll notice that comparison there. Okay, so that's basically what linear approximation is. It's just taking a tangent line and approximating values at the curve, just really close to a value that you definitely know. All right, that'll conclude today's lesson.